Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan, and I am a chemical engineer. Today we will discuss steam strippers. The use of steam to remove lower boiling or lighter components from a liquid is one of the oldest methods of distillation. Sometimes called steam distillation, this technique relies on a combination of two simple effects. Heat of evaporation. The first effect is illustrated when we blow across a bowl of hot soup to cool the soup. Our breath displaces the steam vapors that are on top of the soup. This encourages more molecules of steam vapors to escape from the soup, that is, the vapor pressure of the steam above the liquid soup is diminished, because steam is pushed out of the soup bowl with air. The correct technical way to express this idea is to say the partial pressure of the steam in equilibrium with the soup is diminished. But our breath itself does not remove heat from the soup. The evaporation of steam from the soup, promoted by our breath, takes heat. Converting 1 pound of soup to 1 pound of steam requires 1000 BTU. This heat of evaporation comes not from our breath, but from the soup itself. The correct technical way to express this second effect is, the sensible heat content of the soup is converted to latent heat of evaporation. Example calculations. For example, if we have 101 pounds of soup in a rather large bowl, and cause 1 pound to evaporate by blowing across the bowl, the soup will lose 1000 BTU. This heat of evaporation will come at the expense of the temperature of the remaining soup in the bowl, that is, each pound of soup will lose 10 BTU. If the specific heat of our soup is 1.0 BTU per pound degree F, the soup will cool off by 10 degrees Fahrenheit. A steam stripper, as shown in picture, works in the same way. The diesel oil product drawn from the fractionator column is contaminated with gasoline. The stripping steam mixes with the diesel oil product on the trays inside the stripper tower. The steam reduces the hydrocarbon partial pressure and thus allows more gasoline to vaporize and to escape from the liquid phase into the vapor phase. The heat of vaporization of the gasoline cannot come from the steam, because the steam at 300 degrees Fahrenheit is colder than the diesel oil at 500 degrees Fahrenheit. The heat of vaporization must come from the diesel oil product itself. We can use this idea to calculate the percent of diesel oil that would actually vaporize across the stripping trays in the stripping tower. Let's assume the following thermal properties for a typical hydrocarbon mixture of diesel and gasoline. 0.60 BTU per pound degree F is the specific heat. 100 BTU per pound is the latent heat. Referring to picture, the reduction in sensible heat of the diesel product equals 500 to 475 degrees Fahrenheit times 0.60 is equal to 15 BTU per pound. The percent of the feed to the stripper that evaporates is then 15 BTU per pound degree F divided by 100 BTU per pound equals 15%. Measuring evaporation in the field. Note that we have neglected the heat picked up by the steam in the preceding calculation. Often, the steam flow is quite small compared to the stripper feed, so usually this effect may be disregarded. Unfortunately, we seldom should neglect ambient heat losses. Certainly, if the stripper tower and associated piping are radiating heat from the product, this is not contributing to stripping. To determine the temperature drop due to ambient heat losses, proceed as follows. 1. Check the temperature of the stripper feed. 2. Shut off the stripping steam and wait 20 minutes. 3. Check the temperature of the stripper bottoms product. The difference between the two temperatures represents the ambient heat loss associated with the stripper. Of course, with no ambient heat loss, this temperature difference would be 0. Stripper efficiency. Many side-stream steam strippers of the type shown in picture do not work very well. Operating personnel report that the stripping steam is not effective in removing undesirable lighter components from the stripper feed. Why could this be so? One of the main reasons for this sort of poor stripping efficiency is subcooled liquid feed to the stripper. Liquid drawn from any tower or vessel is assumed to be in equilibrium with the vapor phase in the tower or vessel. We say that the liquid is at its bubble point or boiling point. We say that the vapor in the vessel is at its dew point or saturation temperature. When steam is mixed with a liquid at its bubble point, the partial pressure of the vapor in contact with the liquid is reduced. The liquid then begins to boil. The lighter components of the liquid are turned into vapor and are carried out of the stripper with the steam. If liquid drawn from a column cooled below its bubble point as a result of ambient heat loss, we say it is subcooled. Mixing a small amount of steam with subcooled liquid will reduce the partial pressure of any vapor in contact with the liquid, but not enough to promote boiling. Eventually, as more and more steam is mixed with a subcooled liquid, it will begin to boil. But for a given amount of steam, the amount of vapor that can be boiled out of a liquid will always be less if the liquid is subcooled. In this way, ambient heat loss reduces the stripping efficiency of steam. Wet steam will also reduce stripping efficiency. The water in the steam will be turned into steam when it contacts the hot diesel oil in the stripper, shown in picture. The heat of vaporization for this water must come from the sensible heat of the diesel. This reduces the temperature of the diesel, which also reduces its vapor pressure, which then makes it more difficult to vaporize its lighter gasoline components. I was once working in a refinery that could not meet the flashpoint specification for its diesel product. Flashpoint is the temperature at which a hydrocarbon will ignite when exposed to an open flame. To raise the flash point of diesel oil, it is steam stripped to remove the lighter, more combustible components. I noticed that I could drain water from the bottom of the steam supply line to the diesel oil stripper. I then screwed a steam trap onto the 0.75-inch drain valve on the steam supply line. The stripper bottom's temperature increased by 35 degrees Fahrenheit, and the flash temperature of the diesel product increased from 120 to 175 degrees Fahrenheit. High liquid levels in the bottom of the stripper will also reduce stripping efficiency. A liquid level above the steam inlet will cause the stripping trays to flood. Flooding vastly decreases tray efficiency and hence stripping efficiency. Tray deck dumping also greatly reduces tray efficiency. Unfortunately, steam strippers can have widely varying vapor rates between the top and bottom trays of a column. Vapor distribution in steam strippers. This picture shows the type of hydrocarbon stripper discussed above. Note that the vapor load to the bottom tray is only the 3,000 pound per hour of stripping steam. The vapor load from the top tray is 15,000 pound per hour. In other words, the vapor leaving the top tray of the stripper consists of 3,000 pound per hour of stripping steam plus 12,000 pound per hour of hydrocarbon vapor. From the designer's point of view, the top tray of the stripper should have several times more sieve holes or valve caps on its tray deck than the bottom tray. If, however, all the trays in the stripper are identical, then either the bottom tray will leak or the top tray will flood. Either way, stripping efficiency will suffer. Steam stripping water. So far, we have been discussing the stripping of hydrocarbons. But of equal importance is steam stripping of aqueous streams such as removing benzene from seawater, removing ammonia from sour water, removing hydrogen sulfide from amine solutions, removing methanol from wash water, removing oxygen from boiler feed water in derators. This picture shows a simple sour water stripper. The steam is used to remove NH3 and H2S, dissolved in the waste, or sour water. In the diesel oil stripper, discussed before, all the stripping steam went out the top of the stripper. But what happens to the stripping steam in a water stripper? It is used in 4 ways. 1. A large portion of the stripping steam is used to heat the wastewater feed, as shown in picture, from 180 to 230 degrees Fahrenheit. Almost all of this heat comes from the latent of condensation of the stripping steam, and very little of this heat comes from the temperature, or the sensible heat content, of the stripping steam. This means that the wastewater is heated by 50 degrees Fahrenheit by condensing steam inside the stripper. 2. A portion of the stripping steam is used to break the chemical bond between the water and the H2S and NH3 in the wastewater. When these gases first dissolved in the water, heat was evolved or released. This is called the heat of solution. When these same gases are driven out of the wastewater with the stripping steam, this same heat of solution has to be supplied. Again, this heat comes from condensing the stripping steam in the water flowing across the trays in the tower. 3. Some of the stripping steam condenses in the overhead condenser, as shown in picture. The condensed steam, which accumulates in the reflux drum, is totally refluxed back to the top tray of the stripper tower. For a small amount of the stripping steam remains as steam and leaves the reflux drum with the H2S and NH3 vapor product. From this distribution of the stripping steam, we can conclude that the pounds of vapor to the bottom tray are much larger than the pounds of vapor leaving the top tray. This is just the opposite of the diesel oil stripper. Temperature distribution in water strippers. The 230 degrees Fahrenheit stripper bottom temperature, as shown in picture, is simply the boiling point of water at the 10 psi tower bottom pressure. Small amounts of extraneous chemicals, phenol, alcohols, aromatics, dissolved in the stripped water do not change the boiling point temperature of this water. The 200 degrees Fahrenheit stripper tower top temperature is the dew point of the vapors leaving the top tray. Most of these vapors are steam, and that is why the tower top temperature is so high. The high steam content of the overhead vapors cause a water stripper to behave in a strange way. When the top reflux rate is increased, the tower top temperature goes up, not down. This odd behavior is easily understood if we note that there is no liquid product made from the reflux drum. Therefore, the only way to increase the reflux rate without losing the level in the reflux drum is to increase the steam rate to the bottom of the stripper. The extra stripping steam drives up the tower top temperature. The 140 degrees Fahrenheit reflux drum temperature, as shown in picture, is the dew point of the vapors leaving the reflux drum. Almost always, we would like to minimize this particular temperature. The lower the reflux drum temperature, the smaller the amount of steam in the off-gas. If the off-gas is H2S and NH3 flowing to a sulfur recovery plant, the steam carried into the sulfur plant reduces the sulfur plant's capacity and efficiency. On the other hand, a low reflux drum temperature increases the solubility of H2S and NH3 in the reflux water. As the concentration of H2S and NH3 in the reflux increases, the stripper has to work harder to keep these components out of the stripped water. Reboiled water strippers. Many water strippers are initially designed with steam reboilers, rather than with open stripping steam. The amount of steam required is the same in either case. The great advantage of the reboiled stripper is that the steam condensate is recovered and recycled back to the boilers. When open stripping steam is used, the steam condensate is added to the stripped water, thus increasing the plant's water effluent. Hence, the use of open stripping steam is environmentally unfriendly. Fouling is the main reason for abandoning many stripper reboilers and substituting open stripping steam. It is easy to pipe up steam to the stripper. It is difficult to determine and control the cause of the fouling in the reboiler. But not to find and control the cause of the fouling is sloppy engineering and poor operation. Stripping aromatics from wastewater. Removing benzene and other aromatic compounds from a plant's effluent water is an increasingly common environmental requirement. This is typically achieved with a steam stripper. There is a rather neat trick, which can increase the stripper's efficiency, adding salt water to the stripper feed. Aromatics, especially benzene, are far less soluble in brine than they are in fresh water. But, of course, the brine will be more corrosive than salt-free fresh water. Side-stream stripper hydraulics. In a project, a young engineer was to improve the quality of jet fuel from a side-stream stripper. Initially, he had thought the problem was due to poor stripping efficiency, but it was really a simple problem in hydraulics. the part of technology that deals with the pressure drop of gases and liquids flowing through pipes and other process equipment. Liquid heads, gravity, and friction are all parts of hydraulics. The particular problem he encountered is illustrated in picture. The jet fuel product was steam stripped to remove a lighter naphtha contaminant. But much naphtha was left in the jet fuel. Apparently, the packing in the stripper tower was not working properly. However, a discussion with the unit operator indicated that they were using very little stripping steam. Introduction of a normal amount of steam resulted in a loss of liquid level in the bottom of the stripper. The pressure at point A in picture was 13 psig. This means that the pressure drop in the vapor line from the stripper back to the fractionator was 3 psig. In order for the unstripped jet fuel to flow out of the lower pressure fractionator and into the higher pressure stripper, it had to overcome this 3 psig pressure difference. The 16-foot elevation difference between the draw-off nozzle on the fractionator and the stripper inlet provided the necessary liquid head driving force. Let us assume that the specific gravity of the unstripped jet fuel was 0.59. Also, note that for water, which has a specific gravity of 1.0 psi of pressure equals 2.31 feet of water. This means that the pressure head of a column of water 2.31 feet high equals 1 psig. The height of a column of unstripped jet fuel equal to a pressure head of 1 psig is then 1.0 psi is equal to 2.31 times 1.0 divided by 0.59 is equal to 4.0 feet of jet fuel. The pressure head of the column of unstripped jet fuel 16 feet high, as shown in picture, is 16 feet divided by 4 feet for psi equals 4 psi. This means that there was a 4 psi pressure head driving force available to overcome the 3 psi pressure drop of the stripper's overhead vapor line. This was sufficient for the jet fuel to flow out of the fractionator and into the stripper. Raising the steam flow to the stripper increased the pressure drop in the overhead vapor lines from 3 to 5 psi. The pressure at point A in picture then increased from 13 to 15 psig. The 4 psi pressure head driving force was not sufficient to overcome the 5 psi pressure drop of the stripper's overhead vapor line. The unstripped jet fuel could no longer flow out of the fractionator and into the stripper, and the liquid level in the stripper was lost. To correct this problem, he designed a larger diameter vapor line connecting the stripper to the fractionator. Pressure drop through piping varies as follows. Delta P new equals delta P old times old pipe diameter divided by new pipe diameter, caret 5. Changing the vapor line from a 3 inches pipe to a 4-inch pipe reduced the line's pressure drop from 3 to 0.7 psi. This permitted the stripping steam flow to be increased to the stripper, without impeding the jet fuel flow from the fractionator. The higher stripping steam flow efficiently removed the contaminant naphtha from the jet fuel product. Liquid line DP. The liquid head driving force of 16 feet, or 4 psi, as shown in picture, is actually not all available to overcome the higher stripper pressure. The frictional loss of the piping used to feed the stripper should be subtracted from the liquid head driving force. In the jet fuel example presented before, this frictional loss was neglected. Sometimes the cheapest way to correct a hydraulic problem on a side stream stripper is to pump the product into the stripper. But leaving the pressure in the stripper high will reduce stripping efficiency. That's all, gentlemen. If you like my video, please follow my YouTube channel Petro Intelligence for more videos. Good day and good luck.